The next problem I'm going to work is a pressure temperature problem, which is Gay-Lussac's law. But really, I don't even need to know that. I just need to know what they give me. So in this case, they tell me that I have 150 psi. Psi, kind of a weird unit, so we know it's pressure. So I'm going to call that P1. Then they tell me that it's at a temperature of 25 degrees Celsius. Remember, we cannot work the problem until we're in Kelvin. So you have to be okay to work the problem. And then they're asking me that what's the pressure in the tire if I actually take it to a cooler environment. So I'm looking for P2, and they're giving me a temperature T2. And the temperature T2 is minus 5 degrees Celsius. So again, we're going to add 273. It's going to end us up with 268 Kelvin. I'm assuming the bike tire can't change that much in volume, so we're going to keep our volume constant here. And so what is happening to temperature? Temperature, obviously, is going from 298 to 268, so temperature is going down. And remember that pressure is a result of the molecules hitting the sides. They're going to kind of cuddle. They're cold, so they're going to reduce the pressure, not hit the side of the tire as much. So your pressure is going to go down. And often, on a really cold day, your tires can actually look flat when this happens. So I need to find a new pressure at this new temperature. So I'm going to start with the original pressure and come up with my fraction of temperatures to determine that. So my answer needs to be lower. My choices to go on top and bottom are 268 and 298. So I want it to be lower, so I need 268 to be on top. So 298 will be on the bottom. And so when I work through this, actually work out the problem, I end up with 94.4 psi. And then I double check, and yes, 94.4, 105, it is lower, so that is my P2. Now, I could have worked this problem another way. I could have used the formula. So the formula, when temperature and pressure are related, is P1 over T1 because it's direct, P2 over T2. An easier one to work is to actually move the temperatures, P1, T2, P2, T1. We would plug in everything and just solve for P2. And you can work it that way. Now I'm going to do another problem, but this one is not going to have anything constant, but just the particles. So I'm going to look again and label everything that they give me. I'm going to label all my numbers. So I'm given a centimeter cubed, well, that's a volume, so I'm going to call that V1. I'm given a temperature, 25. But remember, just do it instantly. Can't be, I'm not OC, I'm okay, so I've got to convert it to Kelvin. And I'm also given a pressure, 730 millimeters of mercury. But what they're asking me to do is change these, and often we'll do this in labs, is to just adjust everything to standard conditions. Well, standard conditions, STP, is standard temperature. So my standard temperature is 0 Celsius, which I'm going to convert to Kelvin. So I know that my standard condition is 273 Kelvin. And then I also need standard pressure. The P stands for pressure. To find standard pressure, we're going to use one off the pressure list. This is the standard pressure list. They all equal the same value. They just have different units. So which unit do I want to use? Well, I'm going to choose one that's going to make my life easier. So I look and I see my original pressure is a millimeter of mercury, so I might as well make my new pressure, the standard pressure, also in millimeters of mercury. So I'm going to choose 760 millimeters of mercury. So now pretty much everything I need. And what I want to do is figure out what my fractions are, what I have to use. I'm looking for a volume. That's my question mark. So I'm going to start off with my volume, my 250 centimeters cubed. And I know it's going to be affected by two different things that aren't affecting each other. And that is the temperature and the pressure. So I have two separate fractions to deal with. So what that's going to do is I'm going to have two fractions that are going to help me reach my answer. So first of all, I look at the temperature. Well, temperature is going from 298 to 273. So temperature is going down. So temperature is down. Well, whenever temperature is down, volume decreases because everything kind of gets closer together. And so I possibly will decrease my volume depending on the pressure. So based on temperature, volume should go down. So what number should I put on top? The smaller number. We'll put the 273 Kelvin over the 298 Kelvin. Again, my goal is to end up with centimeters cubed, so all my units other than the centimeters cubed better cancel. So now I'm going to do the same exact thing for my pressure. What did my pressure do? From 730 to 760, pressure went up. But what do we know about the relationship between pressure and volume? Well, volume will go down when something is squeezed. So again, the result should be a lower volume. So based on pressure, to make my answer lower, I need to put the smaller number on top. Also, I'm going to notice that my units must be the same. So both of these have to cancel. So then I'm going to just basically do the math. 250 times 273 times 730. To get that answer, I'm going to divide it by 298 times 760. Be careful, use your parentheses when you work that problem when you're putting in your calculator. I know that this is in centimeters cubed. Everything other unit has canceled out. And so for this one, I end up with 220. I think if we round it, it's 221 centimeters cubed. And I could have used a formula. The formula for this one is vice president V1 P1 over T1. I kind of call it vice president over treasurer. And then V2 P2 over T2. That's a combined gas law. Now we can move it to make it more friendly and make it V1 P1, put the T's on the wrong side. Be careful though if you use the formula to plug in the T's in the correct place. In this case, I would have plugged everything in, isolated V2, and I would have my answer. So you can either do it formula-wise or you can do it fraction-wise.